Okay.
Okay. Hello.
Okay. Hello.
Hello.
Hello, everyone. Good afternoon and good evening. My name is Yao Fanjun. I'm a PhD student in Tsinghua University. My tutor is Professor Gao. The title of my presentation is Study on Low Carbon Supply Chain Coordination, Considering Reference Emission Reduction Effort. My presentation have 6 parts. Is the introduction, model description, model analysis, comparative analysis, numerical examples, and conclusion. Sorry. In this list, you can see several carbon levels. This is China and Taiwan. Taiwan is the levels, and this is the America, Japan, and Germany and France. There is the Coca-Cola is familiar with us. In this bottle, there is the carbon level, and this is our government working with the carbon trust. It means that if a manufacturer produce this garment, he will emit 2.4 kilogram carbon. And this at present, global warming and climate emergencies are a cause lot of concern to all parties, such as the greenhouse effect cannot be ignored, which affect the sustainable development of the global economic. In order to improve the living and production conditions and achieve the so-called green low carbon life, low carbon green policies and supply side low carbon reform are necessary. These 2 pictures is this is the manufacturer such factor. This is the airplane. It's common in our life. And this is the these two pictures is the Couture-Patino and Paris agreement. This is 2 policies in all over the world. In terms of policy, the Couture-Patino and the Paris Agreement were signed, and many countries and regions have now established various kind of carbon policies according to their industrial development and emission reduction goals. For example, the European has included the international aviation sector in the European carbon emissions trading system. And on the demand side is ourselves for everyone. With the advent of the low carbon area, consumers' environmental awareness is further enhanced. Low carbon tourism and low carbon consumption have become new fashions. These 2 pictures, the set of those pictures is familiar with us and is previous. It's the transportation and this is the electronic, and this is to buy something in a green style. Just the online buy O2O. Consumers' low carbon preference is not only affected by the current promotion and emission reduction, but also by the previous consumption promotion and emission reduction, which is generally characteristic by the reference effect. The reference effect is based on previous experiences with the product and the evaluation of gains and losses from a base or expert level. Therefore, taking account of the reference emission reduction effect, we use the differential game theory to solve the supply chain emission reduction problem. This is the second part, is the model description. The first notion is the reference emission reduction level. We assume that the consumer reference emission reduction level, RET, depends on the low carbon goodwill, GT, of the product, and the consumer experiences with good low carbon goodwill to have higher emission reduction. Namely, it's just this equation is RET equal to CGT. The KC represents the carbon emission low carbon goodwill correlation coefficient. And two, the notion is low carbon goodwill. We assume that the reference emission reduction and permission also have a positive effect on low carbon goodwill, refer to the classical goodwill dynamic equations of Nero and Aru, 1962, characterizing the dynamic of low carbon goodwill as this equation. Dot dt equal to z multiplies t minus ret plus eta t minus dt. D0 to D0 is the initial low carbon goodwill at time 0. And this is the important part. And Z multiplies the ET minus IET reflects the impact of the reference emission reduction effect on low carbon goodwill at time t, which implies that low carbon goodwill is positively affected when the manufacturer's emission reduction is higher than the reference reduction and negatively affect others otherwise. AT is the promotion at time t. This is the retailer. Z and H are the coefficients of the reference emission reduction effect and the promotion on low carbon goodwill, respectively. Z is the natural decline rate of low carbon goodwill, usually due to the impact of new product launches and consumer forgetting. Substitute equation 1 into equation 2, and with the notion and delta equals to sigma minus this. The dynamic of low carbon goodwill can be written as this equation. Now is the demand function. Assume that the consumer tend to buy products with higher level of emission reduction, good brand, and low prices. It's common knowledge. For example, if I want to buy something, now I will locate is the green and is the carbon emission level. The market demand is influenced by consumers' low carbon performance, retailer price, low carbon promotion, and low carbon goodwill. We divide the market demand influencing factors into price and non-price, and they influence the demand through separate multiplication form. Therefore, the product market demand function is dt equals to gamma multiply dt multiply r minus beta p. The pt is the retailer price at time t. Gamma and beta stand for the low carbon performance coefficients and price sensitivity coefficients of consumer respectively. I for is the market size, and R minus PT is bigger than is negative. This is a cost function. Assume that the unit production cost independent of emission reduction is a constant C according to the general cost capacity assumption. The manufacturer is emission reduction cost function and the retailer's promotion cost function at time t can be expressed as this. The cost percent is non-negative and promotion cost respectively. This key M and key R. Now is the objective function. Assume that the manufacturer and retailer have complete information and made reasonable decisions without considering inventory out of stocks. And if origin, the manufacturer and the retailer have the same discount factor. Thus, the long-term profit of the manufacturer and the retailer respectively are like these two equations. The time is from 0 to infinite. This is the discount factor. For the manufacturer, the ohmic T, ohmic minus C is his marginal profit is equal to, this is the demand function, gamma dt. This is affect the demand. Now minus the cost function. Similar, this is the retailer's objective function. The distinct is that it is the PT minus OT. This is the retailer's cost function. In the third section is the model analysis. The first model is the centralized decision making. Maybe we note is the notion is the model C. The objective function for the analysis is the model C. The manufacturer and the retailer form or alliance. They will joint to decide the three variables. ET is the emission, AT is the advertising, such as the advertising, the promotion, and the PT is the retailer price. In this model, there is not ohmic T. It's just is the retailer price minus the cost. Multiply the demand function minus the two cost function. And after the calculation is the stream one is the equilibrium strategies in the model C is just like this. EC, AC, and PC is equal. Is the arithmetic solution, and the evolution of log half goodwill is this: DCT equal to D0 minus G, and infinite. This is the steady state of the goodwill in this model. Multiplies E power minus delta T minus this is a steady state, where the steady state G ohmic C is this equation, and the total profit of the supply chain it includes the manufacturer and the retailer is the value function is VCD is equals to this C multiplies DC minus plus C2, where C1 and C2 is this. Similarly, this is the decentralized decision making. We call it the model D. Similar, this is the equilibrium strategies. In this model, there have ohmic D is the is the strategy of the manufacturer. This is decentralized. The player made their strategies independent. This is the advertising. This promote the PT. Also, this is the evolution of the lock-up goodwill in the Model D. With the similar, the difference is that the steady state of the lock-up goodwill in the Model D is like this. In this model, the value function of the manufacturer and the retailer is independent. This is the manufacturer's value function. Each one and each two is equal to this, and the retailer's profit is like this, and this is the L1 and L2. The most contribution of our paper is this, is the cost sharing decision making. We call it Model CS. In the Model CS, a cost share contract is adopted between the manufacturer and the retailer, between the players, where the manufacturer shares a portion of the retailer's promotional cost. We call it is a meal to increasing incentive the retailer the promotional incentives. The design problems of manufacturer and retailer is like this. For the manufacturer, in the CS Model CS, here we have three design strategy, three variables: ET, OT, and this is the mu T is the share of the retailer's cost. This is just is the same with the Model D, and the only difference is that the manufacturer share mu multiply the retailer's cost function, and this is for the retailer is the one man his retail function. And
杨老师时间不太多了，您可以稍快一点。
This is the equilibrium strategies of this model and the evolution of the local goodwill. This is the profits of each other. This is the cooperative analysis. Is the 3 and 4 is the on 3 was the relationship between the and the retailer's promotion price is the relation is like this. The relationship of lock-up goodwill under the 3 model is this. The centralized is the biggest, and the cost share is bigger than the decentralized. This is the numerical examples. These the parameters, and this is the sensitivity analysis of rho and gamma. In this picture, in model CS and model D is equal in this picture, and for the promotion in the 3 models is like that. The model C is bigger than the CS and bigger than the model D. It's the dynamic trajectories of carbon goodwill. The CS is the red. Is this? It's bigger than the model D, and this is the dynamic trajectories of reference emission reduction. This is the dynamic trajectories of supply chain profit. This picture is the manufacturer's profit. The red is the model CS, and this picture is the retailer and this is the supply chain profits. This and this plus this. Here is the conclusion. No matter what level the initial value is, the supply chain members, through scientific decision-making, low-carbon goodwill, and reference emission reduction, can converge to the corresponding state, indicating that the initial value of low-carbon goodwill or reference emission reduction does not affect its steady state, which is determined by the supply chain members' different strategies. And compared with Model D, the manufacturer's cost share contract has no effect on emission reduction and retailer price, but rise the retailer's promotion and thus enhance low-carbon goodwill. The retailer price and the two models of decentralized and cost share remain unchanged, and the increasing in demand brings about an increase in profit, which eventually achieve profit parity, improving and increasing social welfare. In actual operation in the supply chain, Model C has attracted much attention because of its high operational efficiency, but difficult to achieve due to the diversification of the members in the supply chain. Model D is common, but the double marginal effect inherent in it seriously damages the operational efficiency of supply chain. Therefore, this picture uses cost share contracts to coordinate the low-carbon supply chain. And it found that the cost share contract can effectively alleviate the double marginal effect of low-carbon supply chain and improve operational efficiency. Thank you. Thank you very much.
Thank you.
Thank you very much. A very interesting presentation. I'm interested. If no one has any questions, I have several.
I have one. Can I ask one question? I wondering if you find Nash equilibrium or the Steck equilibrium in sharing scenario.
Yeah.
So, do you find Nash equilibrium or Steckenberg equilibrium?
Steckenberg equilibrium.
Steckenberg.
Yes. In this paper, the manufacturer is the leader and the retailer is the follower.
And do you take into account that the price may be negative? So if they choose equilibrium strategies, the price may be negative. Do you take into account this condition or not?
Yes, condition is non-negative. Is
non-negative.
Yes.
Okay. Thank you.
Thank you.
So any more questions? So I have a question about the general assumption in the model. So you say that the players or the agents, they have full information about the motion equations and payoff function for the whole interval from t0 to plus infinity, right? And you have another assumption that not the assumption. So the purpose of your work, as far as I understand, is to model of what will happen in the future, right? To model the strategies and then to model of how the what policy is better for controlling the CO2 emission, right? So as far as I understand, it is like this. So you use this model to forecast the behavior of players and then to choose different controlling models, right? But I have a question. Yeah. So I have a question. Not actually, it's a question slash proposal. So what do you think if you add into this model a kind of restricted information for the player, such as of course players or companies or I don't know exactly in this model, so they cannot forecast their actions from this point to the infinity. and usually people do not do it. In different types of business plans, companies orient themselves maybe 5 years or 10 years, not more. Of course, they have long-term goals, but it's very hard to keep in mind all these goals. So I have a question, and
Yes.
if you want to apply for this model the so-called continuous updating approach, this is the approach that I'm working on, and it helps to model the behavior of players when they have this restricted information. And we can also help you to, if you want, to obtain the results for infinite horizon, and to obtain result in the case when time equals to infinity. So when for yeah, so we can try to solve. If you will be able to send us some materials about this work, we could help you to see whether continuous updating approach will give you even more information about the problem that you consider. If you want, that would be very great. Oh, okay. Thank you very much.
It's my pleasure. Thank you. Thank you.
Thank you very much. Thank you very much.
Thank you.
Maybe at the section of control theory, there will be one presentation. I will be doing it, and it's not related to differential games, but it's related to continuous updating approach. So maybe you will understand some. I hope it will be clear. So some of the key points. Okay. Thank you very much. Thank you.
Okay. Thank you.
Do we have? If we don't have any more questions, we can go to the next presentation. So sorry. So the next presentation is the presentation of Professor Yelena Parilina. The title is Dynamic Games with Stochastic Components and Uncertainty. Okay. Thank you.
Share the screen. Okay. Thank you very much, Vanessa, for inviting me here to present my work. It is only the description of my work in this area of dynamic games with stochastic components and uncertainty. And I will briefly describe the recent results and the possible directions of future research. So the recent publications that are submitted but not published, I will describe the ideas that I realized with my courses in this area. So I would like to say that these works are made. All these papers are published with my courses. Stepana Kimachkin, Elnas Kanani, it is not published but submitted, and Leon Petrosyan, Artyom Sidakov, Alexander Tempieri, and George Zakur. So I would like to say that this amount of publications there can be divided into two sub-areas. So the first part, it is devoted to the works on games played over event trees, and the key point here is that the player's actions do not control the transition probabilities from state to state. I will describe clearly this type of games. And the second part of this work is devoted to cooperative stochastic games when players control the transition probabilities from state to state. So the first part, it involves the simplified dynamics in comparison with the second part of works. And the first part is devoted to dynamic games played over event trees, and I will describe a bit how these games are realized and they are given. So we can imagine the tree, and it is called an event tree, and we assume that we have the finite set of players, and we assume that we have some stochastic process or some uncertainty that can be represented on a tree. The tree has a finite length, So we have the finite set of periods, and we assume that we start from the initial node n0. And at this node, players choose their strategies or actions, and they get their pairs. And after that, after the realization of the actions and getting the pairs, the stochastic process transits to some other nodes. Yes, we have here at time period 1, 2 nodes, and at these nodes again, players choose their strategies and they get payoffs and so on. And here we should mention that the players' payoff functions can depend on the nodes, so they can differ from node to node. And also the state variable, we have here the state variable, it depends on the node. So the transition can be different if we go here or here. We have different state variable realizations. So the feature of this event tree is that we have the uncertainties, but we know the probability distributions about this uncertainty. So it is given beforehand. So before the game starts, we know the probabilities of transition from one state to another state. And the feature of this event tree is that we the actions of the players that they choose at each node, they do not influence the probabilities of transition from state to state. These type of games are very popular in business and in economics modeling because for example, you can imagine that we have some economics and it is represented, the economic situation can be represented by a tree, and you can go here and get, for example, bad realization of economics parameters, and here good realization, and so on. So it is usually used for economics, like the trees, like binary trees. They like to have two possibilities, good and not good, for describing and to take into account to make a decision at each time period. So on this type of games, I considered, so I listed some recent results about this and describe what has been done in this area, and I describe some results in this game. So in the first publication with George Zakur, we constructed a core. So we considered the cooperative version of this game and constructed a core and proposed the node decomposition of the elements from the core, initially proposed by Leon Petrosyan for differential games. And we adopted it for this type of games. And we proposed the conditions for this type of games, how to sustain cooperation, sustain the imputations from the core, and illustrate the results on an example of pollution control. The next publication, again with George Zakur, was devoted to the construction of an equilibrium which supports the cooperative behavior of the players. So in this publication, we assume that players cooperate, that they realize cooperative trajectory, but this trajectory can be not subgame perfect in the game. So for example, we need to realize some strategies at each node. We know this, but individual deviation can be realized. And we suggested a method how to construct subgame perfect epsilon equilibrium, and suggested a method how to find this epsilon based on the payoff function and probability distribution given on this tree. And the next publication, again with George Zakur, was devoted to the strategic support of the cooperative trajectory. But here we assume that on cooperative trajectory, players redistribute the payoffs and they adopt a node consistent scheme, so imputation distribution scheme. And again, we construct the subgame perfect epsilon equilibrium. And in the next publication 4, we consider, with George Zakur, we consider the Shapley value, but we add the randomness of the so at each node, we have the positive probability that the game will stop at this node. And in this case, we needed to connect two possibility computation of this procedure at each node in case the game ends or does not end at this node. So there are some like modification of the previously given imputation distribution scheme for this type of games. The fourth publication, it is the course publication with Artem Sidakov and George Zakur. We consider the simplified games. So we consider the dynamic games with linear state dynamics. It is linear state in payoff function and also in dynamics. And for this simplified class of games, it is not linear quadratic, so it is much simpler to find the solution here in an explicit form. And we considered a binary tree. And we also got a simplification that the probability of go to the left or to the right does not change over time. So it is always P and 1 minus P. So we consider this class of games and with symmetric players, which have the same payoff function. And for these symmetric players and this type of games with binary event tree, we get explicit results for the cooperative solution for the Nash equilibrium. And we also calculate the price of energy for this class of games and find the lower and upper bounds and get some nice sensitivity analysis of this price of energy for this class of games, depending on the parameters of the game. The last two papers are recent publications that they're not published yet. And the first one is devoted to sustainability of cooperation for this class of games when players have asymmetric beliefs. So all players have not the same, but different probabilities of transition from one state to another state. So you can imagine that each player has his own expert and his own information about this transition probabilities over event trees. And we consider cooperative version of this game. So the players first, they cooperate and they find them something like aggregation of probabilities, and we propose different methods how to aggregate these probabilities, and after that they play in cooperation on this event tree, find the cooperative solution. And we in this paper used Nash bargaining solution to redistribute the payoffs of the players in cooperation. And the last application, this paper is due to the application. It is written with Ilnaz Kanani and George Zakur, and it is devoted to the application of this theory to supply chain management. And we considered a cost revenue sharing scenario and for the closed loop supply chain. And we adopt this scenario for, again, event tree, and got some results about the Steckelberg-Nash equilibrium, and got some sensitivity analysis and numerical simulations for this results. And the second part, I will translate to the second part with a bit more complicated stochasticity. I called it like stochastic games because here in this part, players' actions can control the transition probabilities. They influence the transition probabilities from state to state. Here in this class of games, first chance moves and find the proposes the first state for stage one, and it is one state of nature from this, for example, T states, possible states. After that, players, when the state is chosen, players choose their strategies, get their payoffs, and then they transit. So the process transit, the game process transits to the next stage, and to some of the states from the same state as before. And you see here the transition probability, it is a conditional probability from the action that players choose at the previous stage. So we may have a finite horizon or infinite horizon, and there are different possibilities. I also have some publication on both. And I only explain some recent results about this. So the first publication is devoted to the construction of stable cooperation in stochastic games. So the method of construction, the cooperative version of the game, and there are always also the condition of stable cooperation. They are found, they were proposed in the paper by Leon Petrosyan and Nikolai Zinkevich, and I adopt this stable conditions of stable or principles of stable cooperation for this class of games. And they include subgame consistency, strategic stability, and rational behavior proofness for the cooperative agreement. In the next publication, co-authored with Alessandro Tampieri, we consider discounted infinite horizon stochastic games, and we built cooperative version of the game and analyze the conditions under which the cooperative solution is stable, discuss the existence of stable cooperative solution, and consider some types of stochastic games in which the solution exists, and discuss the principle of stable cooperation for this class of games. The next publication, publication 3, it is only the survey of the two classes with infinite and finite horizon on the cooperative stochastic games, where the results of my courses and me are described. The next publication 4, it is the publication courses with Leon Petrosyan. We proposed strongly, it is a refinement of subgame consistency, and we propose strongly subgame consistent core for stochastic games. So we consider stochastic games defined on finite tree graphs, and we construct the cooperative version of the game, find the core, and we also define for this class of games strongly subgame consistent core. And we proposed the method of designing cooperative distribution procedure, and we get sufficient condition how to do it, how to construct a cooperative distribution procedure for any imputation from the core to guarantee this refinement. So this principle of strongly satisfying of this principle of strongly subgame consistency of the imputation. The next publication is devoted, it is published in 2090, and it is co-authored with Vladimir Bure. It is devoted to the application of stochastic games to data transition model. And we model the data transmission in the network with a given topology using the theory of stochastic games. We had two players, and they tend to send as many random packages which appear at these nodes as possible to the final nodes through one common node. And this one common node will give us the conflict between players. And each player has a finite capacity buffer for storing the packages, and we suggested the system of costs for sending and storing data packages and the rewards for players. And this process can be modeled as a stochastic game with finite set of states. We prove the existence of the Nash equilibrium and cooperative solution. We find the payoffs of the players in cooperation and in equilibrium, and compare these payoffs using the price of energy in the network. And The publication 6, it is also written with Leon Petrosyan, and it is published this year. We suggested a new simplified methods of defining characteristic function in stochastic game. It is useful to yes, it is useful to apply this method when you want to construct stochastic game. As you know, as you see, there are a lot of calculations that can be done to construct cooperative version and to construct characteristic function. And here we propose a new method, which is based on the construction, on the calculation of characteristic function as maximum values in state games. And it is a great simplification for stochastic game to use this method and to reduce the number of calculations. And we also prove that there is a nice property of this method. If we construct a core based on this characteristic function in stochastic game, this core will satisfy the property of strong subgame consistency. And this is something like a construction of the subcore with this nice property. So it is a nice method for simplification to get some nice properties of the core. And the last paper, it is written and on the submitted. It is the paper devoted to cooperative solution in stochastic games when players are risk sensitive. So they have not only mean preferences, so they are oriented not only on expectation, but also they combine mean and variance preferences, and variance they take into account with some parameters which characterizes the risk sensitivity of the players. So we construct the cooperative solution, find the imputation for this type of games, and I hope it will be published soon. Thank you, and thank you for your attention, and I'm happy if you have any questions.
Thank you very much. Anyone has any questions? Have any questions?
I have questions.
Yes.
Avanes, I have question.
Yes, please.
Lena, as for game on the tree, you obtained the evaluation of price of anarchy. And my question is it possible that the price of anarchy is equal infinity? Of course, it depends on parameters, but is it possible for price
this,
of anarchy be
thank you. Yeah, it is very nice question. For this class of games, no. So of course, it depends on parameters, and if we have some parameters which infinity we get, or some other, because we have we got in an explicit way the price of anarchy, and it depends on many parameters. Of course, it depends on if all parameters are constant and they are finite, we have no problems with this. But of course, I think we have an infinite price of anarchy for some parameters. So we exclude these cases from our analysis for this class of games.
Because for congestion game, there is a general results that price of anarchy is restricted by 3 over 2. So of course it is interesting to find some class of games on the tree in which the price of anarchy will be restricted some level. For example, for binary trees, maybe for some classes.
We also yes.
Maybe it's possible to find some estimation.
Yes, thank you. So we also consider here a binary tree because it was difficult to consider many probabilities. We consider only binary tree here, and with linear state dynamics to get some explicit formulas. And we show some results. For example, if we increase one parameters, so the price of energy increases and so on. So decrease with some parameters and so on. So there is a sensitivity analysis, and of course, if we have a time horizon t tends to infinity, the price of energy also increases, and I cannot say that it is not equal to infinity. Maybe it is equal to infinity.
Okay, thank you.
Thank you.
Thank you very much. I have a question about the paper which is related to beliefs. So I cannot define which one.
This one, sixth one. It is about beliefs.
Maybe. So about the beliefs. So you consider a dynamic game, right? So in this dynamic game, the beliefs are changing in time for the players or not?
No. So they initially they have the beliefs. It means that they have the probabilities of transition over the event trees, and they are given for each player, and they may be different for the players. That is, it means that they have a symmetric about the tree, and we start to play the game. Yes. So each player has his own beliefs, and of course, in cooperation, they first need to incorporate their beliefs, or they need to take, like, you understand this. So they need to incorporate all the beliefs in one tree, and after that, start playing the game. And we propose different methods from opinion, like opinion aggregation theory. They have some methods how to aggregate probability distributions, and we propose this and show that some of methods they give the same the same aggregated probabilities, very close, but some of them they're very different, and so it depends on how you believe to the other players and how to aggregate the beliefs of the other players in one opinion.
Okay, thank you very much. Actually, now I'm working with one of my students with the direction which is called the Bayesian updating, not the continuous updating, but Bayesian updating, when players they update their belief. Currently, we are not able to construct differential game model for it. There are some problems.
Yes.
But dynamic, I think we almost finished. We wanted to present this seminar, but I think it was not perfect. So maybe if you have time, maybe you could participate next seminar, and you could hear something about it. Maybe it would be very interesting to cooperate, because yeah, so it's a kind of idea for Bayesian equilibrium for dynamic games with updating. If it is possible to, if you know how to apply it. I'm not a specialist in this. I just wanted to construct model, but I don't know where it is. See what is important, where it's important to apply it, or I'm totally confused in this.
Okay. I will listen to you to your presentation. Okay.
Thank you very much. Thank you.
Thank you
for a great presentation.
Thank you. Next presentation is Sun Ping. Sun Ping 在吗? Wait a moment. She said her internet not very well, so she restart computer.
Professor Gao, hello. I see you. Nice to see you.
Hello.
Как у вас дела?
Ну, все хорошо.
На работе сейчас, да?
Да. Дома там мешают дети.
Конечно. Я понимаю.
视频好了吗?
Oh, sorry, Professor. My internet is broken just now. Now I'm ready.
Okay, that's fine.
I will share the screen now. Sorry, wait a minute.
You need to push the green button.
Yeah, I know that. I need to set. Yeah. Sorry, wait a minute. I need to leave the meeting and set again.
Okay.
Sorry for this.
We can have some discussion. Очень много участников, Аванес. Прямо потрясающе.
Это все спасибо Линю.
Линь. Здорово, здорово.
Пожалуйста. Очень поддерживаю от профессор Гao.
Да, спасибо большое, профессор.
Здорово.
Спасибо большое. Мы надеемся, что следующий год, когда коронавирус не будет, можно ехать в Циндао еще раз.
Мы очень надеемся.
Давно не был.
Мы уже соскучились.
У нас сейчас градусов 16. Ну, погода прекрасная.
Да.
Тепло.
Тепло.
Вчера в Питере был снег, ну, маленький.
Сейчас уже холодно.
Sorry for the late. Yeah. So can you see my screen now?
Yes.
I can see your screen. Yes.
Yeah, so dear professors and friends, good afternoon or evening time zone. Well, the title of my work today is Dynamic Network Formation with Groups and Incomplete Information. Well, to be honest, we are still in the process of this work. We haven't finished. So today, I will mainly describe the model and talk about the idea and illustrate the results we have now by some examples, and finally show some simulation results. Well, there are some features about this work. First, the game process is infinite and the time is discrete. And the game is of information because process don't know all information about the game, but a player can learn. So there is information updating rule. And also in our game, player set is partitioned into different groups, and the players in the different groups have different properties. So they are heterogeneous. Besides, it's very important that there is a stochastic factor in the process because in each period, a pair of players will be chosen just randomly. Well, before we describe the specific model, we need to introduce some basic notations. First, about networks. Well, in this model, we study an directed network. A vector of a sequence players from I1 to IK is a path between the two players. If for any two near players, there's a link in this network. And two players are connected to network if there exists at least one path between. The length of a is the number of links in this path. And the distance between two players in the network is the length of the shortest path in the network. And also, a component of a network is a maximally connected subnetwork of him. And this set Cij is the set of players with whom player I is connected with. Then about heterogeneous players in the model. In our work, the player set is partitioned into several sets, N1 to Nm, and NL is the group labeled L in this partition. And label is between two groups, very important model because it decides the cost of maintaining or forming a link between players to the two groups. Then we find the utility of pairs from network. Well, we consider two cases, with decay and without decay. Let's see Formula 1. Well, the utility of player I in this network
Hello? 是我掉线了吗 ？Hello？
Pin?
是他那儿有问题，视频那儿有问题。
Oh, yeah, I'm here. Yeah. Okay, I will share the screen again.
Mm-hmm. Yes.
Yeah, okay.
Yeah.
Sorry. And the second item is the costs of player I maintaining all the direct links. And we can see that the function fx is positive and non-decreasing. It means that if the label differences between the two pairs is high and the cost is higher. So we can define the same utility function for the case when there is without decay. Well, now let's describe the specific model, the network formation process. Well, players start with an empty network in the initial period 0. And in each following period, a pair of players will be selected randomly to update the link. Specifically, if in period K, pair IG is selected, and if there is no link IG now, they need to decide whether to form a link. Well, if there is an existing link, they will need to decide whether to delete the link. And AIG equals to 1 if they want to form a link or maintain the link. If it is 0, otherwise cases. And we need to mention that the link is formed or maintained bilaterally. And the game is of incomplete information since if in a period a pair of players is selected, they will not know the cost of forming the links because they don't know the label group the other players in. But each player has his own belief or knowledge. For example, player I thinks there is a probability HIX that the player he didn't know in the group X. And the EI is the expected cost for the player to form a link with a player he didn't know. And also the game is of incomplete information. There is updating rule. It is called simple updating rule. If the players are ever connected, they will know the exact label of each other. Otherwise, their belief or their knowledge just remain on the initial one. Now let's define the strategy of players in. We first some basic notations. I tall is the pair of players selected in this period, and G tall is the network formed in this period. And sigma t is the formation history to period t. And sum t is the set of all the possible formation history to a period t. And this sum is the set of all possible formation histories in the whole game and in the whole game process. Here, BI is mapping from formation history to set of players that player I are ever connected. So it can be called a updating function of player I. And the WG is also a mapping from formation history to the network, which contains all the which is a component containing all the direct links of player J. And the YI is the set of all vectors of BIWG for any formation history and for any player G. So finally, we can define a pure strategy of player I in the game. It is a mapping SI. The strategy of player I gives action of player I for any player he meets and any updated information. Well, below, we will consider a very special case, a very special strategy. And under this strategy, each player will choose the action to maximize his current expected payoff according to his updated learning. Well, these kind of strategies compose a special state equilibrium, which is called the stable equilibrium. Now let's see the definition. A strategy profile S is called a stable equilibrium if for any player I, the action of player I is 1 under the strategy, if and only if the following inequality holds. Well, the left hand of the inequality is the expected payoff, expected utility of player I, if he adds the link or remains his link. And the right hand is the exact utility of player I, if he deletes the link or not form the link. Since no matter the left hand and the right hand are well defined, so we can see that we can get the result that the stable equilibrium defined before last page exists and is unique. So below, we suppose that players play the stable equilibrium in the whole game, and we want to know the network structure formed finally. And here, gamma t is the selection path up to the period t, and GC gamma t is the unique network formed after the selection path gamma t and the complete information if all players play the stable equilibrium, and also for the definition under incomplete information. And what is very important is the updated of all players. Here, BC and the BIC gamma t are all n-dimensional vectors, and the BIC gamma t is the set of players who are ever connected with player I, or the set of players that player I knows the exact group label. See that complete information player I knows the group label of all players. So it is a set of players except I, because we don't consider player I himself now. But under incomplete information, it is an updated function. Now we want to investigate the stability of networks. So we give a definition. When players play the stable equilibrium in the game, and a network called a stable network under complete information, if there exists selection path such that after this path network J appears, and no link will be formed or deleted given any subsequent selection path in the game. And also the stable network can be also defined under incomplete information. Well, as we see that in our game, players are divided into different groups. And the cost of forming a link between players in the same group are the smallest. And we can think about or apply this model to the real life, that players or people in the same community or same city or same country, their communication cost is smaller than the communication cost between people in different countries or different cities. Well, it's very natural to think that players do actions not only for himself, but for the players in the same group with him. So below we consider another very special strategy under which every player will choose the action to maximize the sum of the current expected payoff and of himself and also the players in the same group and connected with him. So these kind of strategy compose equilibrium called group stable equilibrium. We say strategy profile S is called this group stable equilibrium if for any player I one under the and only the following equality holds. Well, the only difference between this equality and compared with the equality former is that we add the payoff of players which in the same group with player I and also connected with him. And also the left hand and the right hand formula are well defined. So we can see that the group stable equilibrium exists and is unique. And below, we also assume that players play the group stable equilibrium. And here I will not explain it anymore here. And so we give some new definition about group stable network. So when players play the group equilibrium, a network G is called a group stable network under complete information if there exists a selection path that after this path, network G is formed and no link or will be formed or silvered, given any subsequent selection path. The same definition can be defined under incomplete information. Well, below, we will consider two examples which can make us have a more clear insight of the model. The first example, there are 7 players and 3 groups. And the cost of different links is given, and the expected cost for players are also given. Here, we consider a specific selection path shown here under complete information and without decay. Players start with an empty network here, and we consider this path. 3-4 is selected. They will form a link because the cost is very low. And 3-1, they will not form the link because it is bigger than 1. And 1-2 will form the link. 2-5 will not form the link. 5-6 will not form the link. 6-7 will form the link. So if we stop here, a network shown here appear. And we continue. For 5, they will form the link because cost is very low. 1-3 will form the link. It is bigger than 1, but it is smaller than 2. And 1-3 form the link. 5-6 also form the link. So for this select, this network is formed. And after our check, it is a stable network. Now we consider the same selection path under incomplete information. This is the empty network players start. 3-4, they will form the link. 3-1, they will form the link. So the cost is very high, but in their imagination, of course, we see their expected cost is low, so they will form the link. 1-2, they will form. 2-5, they will form. And if we stop here, this network appears. Then we continue. 5-6 form the link also. 6-7, they will form the link also. So if we stop here, this network appears. And after our check, it is stable. So, and the same path, if network formed under complete information and incomplete information. Well, what result this example reflect? It's if F1 is bigger than 1, then under information for any player is not isolated. There must exist a link between him and players in the same group. But it is not necessarily true under incomplete information. For instance, we see figure 5. There is no direct link between 5 and 4 and 5 and 3. So there is no direct link with him and the players in the same group. This is the first example. And let's see the second example. There are also 7 players, 3 groups, and other parameters are given. We consider this selection path and complete information and without decay. And this path to here, a network appears. And after our check, it is stable. Now let's consider the path under incomplete information. We see here. This network is the final stable network under this selection path. But what is very important is that in this final network, also it is stable. Information doesn't become complete because player 1, they don't know the exact group label of each other, also player 3 and player 7. So actually, in real case, player 1 should form a link with the player 2, but they don't know the exact of each other therefore. But the very interesting case is that we consider another selection path here. Under complete information, the same network appears. Under incomplete information, this network is formed. Very important.
稍微点，因为有点超时。
好 ，OK. So in this network, the final the network is stable, but the information becomes complete because players 1, 2, 6, 7 knows the real label of other by this network because it is connected and they know all the cases of each other. So by this example, we see that under some parameters, the variety of the stable networks under incomplete is much wider than that under complete information. Well, there's some simulation results. First is about the number of periods it takes to stable network. This is the comparison when there is decay, incomplete information and complete information. This is when there is decay, without decay. And I put the 2 results together in this figure. And a very significant result is that for when there's no decay and complete information, it is the periods is much lower. Well, why is it? Why is this case? Because the result is that, and when there is no decay and under complete information, once a link is formed, it will never be deleted again. Well, it will never be deleted given endpoint path. So this is much lower. Well, here are some future experiments planned for our future research. We want to investigate this problem. And final experiment results. There are 20 players and 5 groups. And this is a results under complete information. We can see that players in the first group and the last group, they are just connected with groups with players in the near group, but under incomplete information, the links are more crossing, and the connectivity of player group is very high. So I think we will do more experiments for these cases. Okay, thank you so much.
Okay, thank you, Sunping. It's a okay.
Sorry. Sorry.
Okay, please.
Okay. So anyone has any questions? Okay, if no one has questions, Елена Mikhailovna.
But it is a course at work, so I will not ask questions to Sunping. So we need We in cooperation. We are in cooperation. So. It is not Nash equilibrium, it is a cooperative solution.
Okay, okay. No, I'm not very familiar with this.
I only can add some comments.
But yes,
I only can add some comments that, Pin made a great job. So it is very nice. She had really great simulations. So she constructed the simulation of these dynamics, path response dynamics and repeated dynamics. So if you look, she didn't show this, but it is really great that it is realized for so many nodes. So you have 20 nodes and you can realize the process of to convergence to the stable network. And the next question will be how it depends on the parameters of the game, on the number of groups and so on. So on the uncertainty and I mean the incomplete information. So this is it will be a future analysis, but now I find her results very, very nice. So I'm very satisfied by her work.
Thank you.
Okay, thank you very much. Thank you very much, Cecilia.
Sorry again for my mistake in the program. Sorry.
No, it's not mistake. So it's great. I mean, if you show this program, it will be great. Everyone will see how it is simulated. It is very nice. Very nice.
Thank you so much, Professor. Yeah,
it's great.
Okay, thank you very much. So the next presentation, the speaker is
Li Guopeng.
Li Guopeng.
Oh, okay. Can you see my slides?
No. Please, Omnas, close your screen, and then he can share his screen. Thank you. Okay.
Now it's okay. Wait me for a moment. Now can you see my slides?
Okay.
No.
Okay.
My name is Open. The topic of my talk is a simple introduction to network economics and its applications. My talk is at an elementary level, so it's easy to understand. But I think maybe it's useful for those who are unfamiliar with the network economics. My talk will have 4 parts. The first part, I will introduce myself and my research interests briefly. And the second, I want to introduce what is the network economics. And third, I want to talk the relationship between game theory and economic and network economics. And finally, I want to share my current research. Oh, okay. I'm a second-year student, second-year graduate student from Beijing Jiaotong University, and my tutor is Professor Cao Zhigang. And my major is industrial economics, and my current research interest is network economic theory and its applications. And the main tools I use is game theory and some simple graph theories. So first, I want to introduce how to represent a network. A social network can be described by the following 2 elements. The first is the player set, and the second is the link set. For example, in the figure, we can see the player set is 1, 2, 3, 4, 5, and 6, and the link set are 5 to 6 and 5 to 4, and so on. We can see G. I'm sorry. We can see G is equal to this. This is a simple sample of a network, but we can easily extend it to a complex pattern. For example, we can assign the direction to the link. Because in many applications, for example, I cite A's paper, but A doesn't cite my paper, so the link is directed. And another way is to the value of the link is not binary, and we can assign a real number to each link. For example, if we want to if we want to build up the trade network, the trade flow is not binary, it's a real number. So where we can use network in economic research, I think there are a lot of fields we can use network. For example, the financial contagion. If we know the financial network detailedly, we can prevent and control the financial crisis. And another field is the informal help. The social network is very important for people to help each other. And the third example is risk sharing. And we can, if we lack of the formal insurance, we can sharing the consumption risk on social networks. And what are people interested in network economics? Maybe I think the following three are very important. The first is, what is a network structure, and how much do we know about it? For example, if we know the trade network in detail, it's useful in analyzing the shocks of trade disputes. And the second area, I think, is how does the network form? Does the efficient network form? The efficiency means that we maximize the social. If we obtain a stable equilibrium network structure, we want to know whether it is far away from the efficiency. And the third area, I think, is how does the network affect people's behaviors? For example, the peer effects and the learning process and the diffusion process. In the third part, I want to introduce the relationship between game theory and networks economics. I think there are two mainstream research paradigms in networks economics. The first is the random networks. The main tool are the probability theory. For example, the people's action are controlled by a simple probability. For example, in the disease network, a patient will a healthy person will be affected by fixed probability. By this simple setting, we can do a lot of complex things. And the second, I think, the strategic networks. The main tool we use is game theory. See a simple question: if I and J are friends, we may be interested why I and J are friends. There are two explanations. The first is that maybe I and J are assigned to the same team randomly, or they are assigned to the same dormitory randomly, so they become friends. And another explanation is that I can bring net positive benefits to each other. I can bring positive utility to J, and so does J. So they decide to make friends. Okay. Let's see another simple example. I want to introduce a simple and natural definition, which is similar to the Nash equilibrium. We say a network G is stable if no any players I and J wants to add a link IJ if IJ is not in G. For example, in this figure, we can say that if the network is stable, 5 and player 5 and player 3 they don't want to add a link to each other. And the second condition is that no any single player I or J wants to delete a link IJ if IJ is in G. For example, if the network G is stable, the player 6 doesn't want to delete the link 6-5 and 6-4. We can see that the definition of stability is similar to Nash equilibrium. It's just a little different. So in network economics, we can apply a lot of a lot of ideas of game theory to networks. So in this page, I want to introduce a simple game on networks. We can the player set is N and the network is G, and the action set is from the negative infinity to positive infinity for each player, and the payoff function is defined by pi I. The xi is player I's action, and this is other players' actions rather than I, and the G is the network, and the delta is the payoff impact parameter, which gives the sum and the magnitude of effect of players' actions to theirs. So we can see a simple our function like this, and vi is increasing on negative infinity to 0 and decreasing on 0 to positive infinity and symmetric around 0. So we can easily know that the 0 is a unique maximum of vi, and wi we can take any shape. So from this payoff function, we can easily know that the best replies of I in other agents is this. If you add this to this, you can get the vi0. And after we get each player's best replies, we can get a system of equations. So we can solve this this system of equations, and we can get the solution. So finally, I want to introduce my own research, which is about the risk sharing in medical crowdfunding platforms. My intuition is that I find that the medical crowdfunding platforms are more and more popular in the world, such as the GoFundMe platform in America and the Shuidichou platform in China. So we can easily know that the medical crowdfunding platform is different from other kinds of crowdfunding platform because other kinds of crowdfunding platforms are two-sided market, but the the medical crowdfunding platform is more like to a social network. So the network is a very useful tool to solve this problem. I am interested in two interesting questions. The first is that why do people want to help each other? And the second question is that how do people help each other? And network is a useful tool to investigate the above questions. And I'll omit some technical details. And my main findings are that my first finding is that when the shock of a disease is very serious, the medical crowdfunding platform will increase the utility of everyone. Otherwise, it will not. And my second finding is that if you have a higher social capital, for example, you have more friends and more close friends, you will get more help when you have a serious disease. And a good news is that my conclusion accords with the reality. Okay, my presentation. Thank you, and thank you for any comments or questions.
Thank you very much. Thank you. Anyone have any questions? Maybe I have a question related to the stability of the network.
This page.
No, the previous one. An example. Yes. This is not actually my main direction of research. Actually, this is totally not my direction of research. But anyway, this is a classical definition of a stable network, or there are some kind of alternatives from game theory about the theory of this kind of stable networks, or not.
You mean this definition of stability?
Yes. Definition of stability of the network. Is it classical, right, or not?
Yes. I this definition from a classical notebook. It's called Social and Economic Networks, which is written by Marshall Jackson, and yes, this is the definition of stability, and you can define the strong stability, which needs more conditions apart from besides these two definitions. You need more conditions, because here I just say that any two players want to add a link ij, but we can easily know that maybe 4 of them want to add links each other.
Okay, thank you very much. Maybe someone who is working on networks could ask some questions, because I'm not.
Yes, I have a question. Please,
Okay.
last slide.
This
last slide.
This
last one. 10. Number 10.
Okay.
Here. Oh, okay, number 10. The last sentence is you said if you have a higher social capital, and you will get help when you have a serious disease.
Yes.
As I understand, it means if you in a social network, in risk sharing in medical platform, you have more social capital and you will get more help.
Right.
I'd like to ask a question about social capital, because you have a higher social capital. It means more friends, but maybe more friends poor. Example,
yes.
very poor.
Yes.
So if you have one friend, his name is Bill Gates, then you will get more help. But if you have many friends, not richer, so what happened in this problem?
Oh, okay. Your question, I think is very interesting and very important. So here maybe I should say that if the social capital maybe means that you have more close friends, and your friends will have higher social capital too. So in the technical part, I define a definition of network which is called Q call. Q call means that do you know the definition of Q call? In network?
Okay.
The Q call is very useful in defining the structure of cooperation. So maybe I should correct here. I think my expression here is not very it's not very concise. Maybe I should correct it. Thank you very much.
Anyone have questions?
If no one has any questions, more questions, so maybe we will try to invite more professors related to this topic. Thank you, and thank you for participating in the seminar. So the next presentation is wait a second, is the presentation of the мне нужна помощь.
Okay.
Maybe you could introduce In.
Yes. 贾之福.
Okay.
Yeah, please.
I will open the PPT.
Presentation of linear quadratic differential game with application to resource extraction problem. Thank you very much.
Okay.
Could you please start sharing the screen?
Yeah. Thank you very much. Do you hear me?
Okay, please.
My name is Jia Zifu. Today, I will introduce myself and my research, and I will introduce a paper, others paper. I'm coming from Nanjing University of Aeronautics and Astronautics. I'm very glad to take a report. This is my research. In my master period, my research focused on variational inequality problems. In my PhD period, my focus on certain differential game. But in this year, I mainly investigated on certain differential equations. These are my papers. This is 1, 2, 3, 4, 5, 6. These papers are my master's period. These papers in this year are published 3 papers. These papers are master period. These papers are PhD period in this year. Today I will report a paper about linear quadratic uncertain differential game with applications to resource extraction problem. This paper recently, I read this paper. I think this paper is very interesting. So I want to share this with others, with everyone. Yes, this paper. This is the abstract. This paper is about uncertain differential game. Uncertain differential game investigated interactive decision-making of purpose over time, and the system dynamic is described by an uncertain differential equation. This uncertain differential equation different from statistic differential equation. In here, I will introduce uncertain differential equations simply. Look at this. Look at the preliminary. Preliminary. In the best of this axiom, normal axiom, duality axiom, additivity. This means this theory is different from probability theory. So Liu introduce a certain process CT is said to be a canonical Liu process. This is about canonical Liu process. This is the uncertain differential equation. This is different from stochastic differential equation. Mainly different is this. In the statistic differential equation, this is dWt or dBt. This is Wiener process or blow Wiener process, but this is uncertain process, canonical Liu process. Yes. Uncertain differential game is the model I will introduce. This paper is about a zero-sum uncertain differential game. This is the model. Uncertain formulation for different game involved a vector valued uncertain differential equation, this, and describe the function used the evaluation. This evaluation different from the probability evaluation because this is the expected value. I defined this. So I will introduce the main idea of this paper. In 2010, Zhu and others produced an uncertain expected value optimal control problem. Look at this. This is a optimal control model subject to this. This is an uncertain differential equation. They introduced the model optimal control, they prove the theorem. Let GTX be twice differential or lane or this. Then we have this. These are the partial derivative of with respect to t and x respectively. And the boundary condition is this. So in 2013, Young and Go defined the feedback not equilibrium for uncertain difference game and present a sufficient condition to get the Nernst equilibrium. Look at this. This is expanded value model. In this paper, they get a sufficiency condition. This theorem is about the two players zero-sum linear conjunctive uncertain difference game had a central point Nernst equilibrium solution if the following rectangular equation had a solution. This proof is very interesting. They use the uncertain calculus in this paper. Uncertain calculus. This is the result of uncertain calculus. This is the point. Taking integration and expectations of this, we can get this. This take expectation is 0, so we get this. Substitute 11 into the 9. They can be introduced this. Yeah, we get the solution. The theorem is proved. This is the proof is very interesting. They prove a necessity condition. This necessity condition, they mainly use the symmetrical matrix. Where K is a constant symmetric matrix. The corresponding system is this. Notice that xt equal to expectation x satisfies this, and uses the fundamental theorem of uncertain calculus. This uses uncertain calculus again. Look at this. X satisfies the following. The following is a regular matrix differential matrix equation. So we can get this. The performance index function equivalent as this. So if the linear feedback control are optimal for two players, zero-sum linear concentric on certain difference game, then the Kanti equation 10 must have a solution. Moreover, the more satisfies this. The proof is very important. So they use the matrix minimum principle. We can look the reference this and this. So we obtain the Hamilton function. This is the main idea. So we can get the TR. TR is a matrix matrix definition. And the joint equation is this. A joint equation. If we get this, we can get the calculation. Notice in above calculation, we use the following formula. The formula is very common. Look at this. Then we can get the conclusion. We can get a conclusion. In this paper, the authors mainly prove two theorem. So they prove a matrix mean theorem as a sufficient condition to guarantee the center point nothing equilibrium in two players, zero-sum uncertain differential game. Further, for the linear concentric case, they derive a sufficient condition and a necessary condition for the existence of a center point nothing equivalent. Finally, they analysis the resource exploitation problem. This is the application. They give the resource exploitation game. Just a simple example. Look at this. They give the differential equation is this: x ln 0 equal x ln, where a denotes the growth rate of resource. The inertial state x ln is given. The uncertain process CT is one-dimensional new process defined or uncertain space. The performance index function is given this. This is extractor 1. Extractor 1 seems to maximize the performance index function, while extractor 2 seems to minimize the performance index function. They give the solution. They give the following Riccati equation. So they get the solution. The other solution of the above equation is this: the center point nothing equilibrium are this. They get the optimum value of performance index function is this. In the future work, we may consider uncertain differential game with jumps. These jumps these jumps nowadays no previous studies have investigated uncertain difference game with jumps. So if we want to continue these differential games, we can continue investigating this model. On the other hand, we make study comparative uncertain difference equation. This paper studies no comparative. So in the future, won't make study comparative uncertain difference equation. These are the points. This is okay.
Okay, thank you very much. Could you
This okay.
Could you tell what is the key difference between uncertain differential equation and stochastic differential equation? What is the solution of uncertain differential equation in comparing with the stochastic differential equation? I think it would be very good.
Okay. This problem is often this problem is often asked by people. So this case, sometimes no samples are available to estimate the probability distribution. For such situation, we have no choice but to invite some domain expert to evaluate the belief degree that each event will occur. Then, for this set theory, offers a appropriate alternatively in the literature. For the strategy game has attracted much attention in the past three decades. For example, this is. But uncertain theory was proposed by Liu in 2007 and refined in 2010. This theory is about how to handle the belief degree. Nowadays, uncertain theory has become a new branch of mathematics. So this paper is based on uncertain theory.
What is the can you say what is the solution of uncertain equation? Such as I know the solution of stochastic differential equation is a stochastic process, right? And the key difference is that it is non-differentiable, right? That is why we need to use some other type of like Ito integral to calculate the solution and so on. But in here, what is the key point? What would be the solution of this?
Oh, okay.
Just briefly, so that everyone understands, because it's a kind of new thing. So I think not everyone can understand what this is. That would be very great, actually, very interesting.
The main difference between stochastic difference game and uncertain differential game is that in the stochastic we often use Eaton formula, but different from the Eaton formula, we use uncertain calculus. Look at this.
Okay, but what? But okay, but let's.
Uncertain calculus.
I know, but forget. Let's forget for a second about differential games. Only consider differential equation. What is the difference? Only in equations, not in games. In equation, like uncertain differential equation and uncertain and stochastic differential equation. What is the difference? In equations, not in games. In equations.
Equations. I don't know what you mean.
Okay. Wait a second. I will ask Lin to help. In.
Yes.
Ты понял мой вопрос или не очень?
Повторите, пожалуйста.
В чем разница между стохастическими уравнениями и uncertain уравнениями? Вот, понимаешь, есть стохастические уравнения, где справа случайный процесс.
Да.
Здесь что? Я не понимаю. Он начинает объяснять про игру, про дифференциальные игры. Я не про дифференциальные игры спрашиваю. Я спрашиваю про дифференциальные уравнения. В чем разница? Почему это разные вещи?
Да. Статические уравнения и другие уравнения.
Вот
Какая
эти
разница
уравнения.
между ними?
Вот эти, да, не uncertain уравнения. Да. Или я не понял.
他想问的是这个，他不是问这个随机博弈啊，他不是问这个随机博弈，他问的是这个随机方程和那个 uncertain 方程它之间有什么区别？
它的区别 ，the difference is this. In the statistic, we use the winner process. But in a certain difference equation, we use the Kano process. This. Look at the model. This is different. In statistic game, we use winner process. But in uncertain difference equation, we use a Kano process. The Kano process is this. Kano process is said to be Kano process if satisfies the three points. 3 points. This is different from the winner process. The main difference is the uncertain distribution. This is the main idea. So this is if we use the kernel process, we call uncertain difference game. If we use winner process, we call the statistic differential game. Yeah.
Okay. Thank you very much. I think it's clear. Yeah. Okay.
Yeah.
Okay. Thank you very much. Thank you. I hope you will be able to participate next month as well. There will be some presentations related to kind of Bayesian games and things like this. So I think somehow it could be interesting for you. Thank you very much. Thank you.
Thank you.
Thank you very much.
Okay. Thank you.
Thank you. Okay, so
There will be no rest.
There was a rest a long time ago. If you can see the program, but we missed it. It was a coffee break for 30 minutes, but actually we missed it. So, but I think it's an open seminar. So if someone wants to have a rest, you freely can have a rest. It's not a problem. I think we have so much participants. The next presentation is a presentation of
Gong Yicheng.
Sorry, is an associate professor from Wuhan University of Science and Technology. The title of the presentation is the Harshani transformation driven by XGBoost and its application on internet loan credit game. So hello, you can start sharing the screen.
OK， 能看得到，但是好像听不到。喂，龚老师能听到吗？
Could you please use the full screen mode?
Oh, okay, sorry. Just like I want, I forgot to turn on the voice. Okay.
Okay.
Please share screen. 您可以全屏一下。
Okay. Hello, everyone. Thanks, Professor and Dr. Lin in St. Petersburg's University for inviting me to communicate with all of you. Today, I will share some work about game machine learning. And my topic is Hasali transformation driven by XGBoost and its application in internet loan credit game. Here, XGBoost means extreme gradient boosting. It is a kind of statistical learning method. And game theory is a branch of mathematics. And I come from Department for Mathematics and Statistics, College of Science, Wuhan University of Science and Technology. Today, I will share with you my work about one problem, second is literatures, and the third is motivation for our research. And the fourth is a framework of XGBoost-driven game analysis. And the fifth branch is about internet leading game. And the sixth is an empirical analysis. And the last one is concluding remarks. Okay, first, let me introduce the problem I research. Our topic is about Hasali transformation. It is a traditional method introduced by Hasali in 1967. And usually we use Hasali transformation to analyze the incomplete information game. For Hasali transformation, the key step is to introducing the virtual player lecture, and then the lecture assign types to real players according to certain probability distributions. Now, a number of researches about the theoretical analysis and the applications of Hasali transformation. But in practice, how to get the probability distribution? So the problem is how to get the probability distribution for nature. Okay, if all the history data is accessible easily, so it is easy to get the probability distribution. However, in many cases, it is rather difficult to get all of a new player's own history data directly. Well, it is easy to get directly a part of a newer player's own history data, and we can easy to get directly all of some older players' history data. For instance, for an internet leading platform, it is difficult to access directly all of the history data and credit type of a new borrowing applicant because this is a secret. But it is easy to access directly all of massive older borrowers' credit data. Then, how to get a new player's credit type indirectly? About this question, some scholars used the AI or machine learning technology. Liu Tieyan and his team in 2013 put forward the concept of game machine learning for the first time at the Artificial Intelligence Congress. By online data and the Markov chain, Xu in 1913 and Liu Tieyan, etc. in 2014, and Liu Tieyan, etc. in 2015, they get some machine learning advertising search bidding ranking model to construct. And the practice, put the model in practice in Baidu, etc. The research shows it reduces advertising and increasing revenue by 10%. And AI game with dynamic scripting are proposed. Another, etc. 22 and Sprock 29, GB 2016 and 2017. The most famous is about AlphaGo, okay, which is 2016. Okay, then how to get a new players type indirectly? We try to get the new players type distribution indirectly by a new statistical learning method, XGBoost, which is desirable for data of large sample and missing values. Based on the predicted distribution, lecture assigns the real players type, and the Hassai transformation can be driven to be practicable. Because the essence of the idea is data-driven Hassai transformation by the learning method XGBoost. So we call our work as a Hassai transformation driven by XGBoost. Okay, this is the framework of our work. First, based on massive old players feature data. Okay, this for old players. For older players, we can get the feature data and also the neighborhood data. Okay, for his credit label. Now, based on massive old players feature data and the neighborhood data, we use XGBoost. We use XGBoost to learn model, learn the relationship model between feature data and the neighborhood data. Okay, so we can get a model type about the type probability model. And based on the type probability model, we can predict a new player. For a new player, we can get just for a new player, we can get just the feature data. For example, his education level and his salary or his city, but we don't know the type, whether he will pay off the credit or not. We don't know. So we just get the feature data for a new player. We don't know the credit. We don't know the labor. So this is a problem to predict. Okay, now we used learned type probability model by XGBoost to forecast the type, okay, the new player's type. And then we used this type probability distribution to direct the lecture. Okay, so the lecture will assign the type of the new players according to the type probability distribution, which is learned by XGBoost. Okay. Just now we talked about the framework of XGBoost-driven hands-on information. And then we talk about the framework of XGBoost-driven game analysis. First, we can construct a model for incomplete information game, and we can do the theoretical analysis for this incomplete information game. We can do traditional Hassani transformation, and we can get the Bayesian-Lassing equilibrium by theoretical analysis. And then, on the other hand, for a new player, we can use the XGBoost model to predict the type, and we give the probability to nature. Then nature will assign the type of a new player according to the prediction, and then we can use the probability to guide the nature to the type assignment, and we do the Bayesian belief update, which will guide the player to do decision. That is the practice. Okay. So a player can update his beliefs of his opponent players and be guided to make better decisions. Okay, next is about the incomplete information internet no-one credit game. The assumption one, the leading platform has only one type, good credit. So this means an applicant believes the leading platform is of good credit with probability 1. So an applicant has only one strategy, apply for loan. Applicant will only have one strategy, apply for loan. But the applicant will have two types. Maybe he will be good. It will be of good credit or bad credit. But for any applicant's application, the leading platform has two strategies: approve or refuse. And the hypothesis 2 is the amount of the loan applied by the application is D, and the assumption 3 is the loan interest rate is R, which is a simple annual interest rate. And the next hypothesis is the opportunity cost is considered in every case. So for the application of a good credit applicant, if the leading platform approved the application, then the leading platform will get will earn the profit RD will rate interest, and the D is the amount of loan. Okay, but if the leading platform refuses the application of a good credit applicant, then it will lose the chance to win the profit RD. So for the leading platform has a payoff law will be negative RD. But if the applicant is of bad credit, then we know if it is the applicant is of bad credit, but the leading platform approved the application, then the leading platform will lose the interest RD. So its payoff is -1 plus R times D. But if the lending platform reviews the application of a bad credit applicant, then the leading platform will avoid the loss of amount D. So in this case, the platform will get the payoff D. Okay, so that's about the internet loan credit game, and we can do theoretical analysis by Hessani transformation. Suppose the probability distribution of an applicant's credit type is PG and 1 minus PG on type space good credit, bad credit. By introducing the virtual player nature, the extended game after Hessani transformation can be shown as this figure. First, the virtual player will nature will assign the type to the new applicate good credit by probability PG and the bad credit by probability 1 minus PG. And then the lending platform can choose his strategies, approve or reviews. Okay. And by theoretical analysis, we can know the expected payoff of the lending the internet finance enterprise or the lending platform is PG, because if he choose approve, then his payoff depends on the type of the applicant. If the applicant is of good credit, so is of good credit, then he will get RD. But this event only take in the probability PG, so PG times RD. And if the applicant is of bad credit, then when the platform approve, it will get -1 plus R times D. But this event happens only within the probability 1 minus PG, so 1 minus PG times this one. So we can vocalize this formula into this one. And similarly, we can get the expected payoff of the internet financial enterprises when he choose the strategy reviews. Okay, we can do this one. And theoretically, we can get if E approve equals E reviews, we can get PE. The probability of equilibrium is R plus 2 over 3 R plus 2. Okay, and because we know if the platform gets the probability PG directly, it would better approve if PG is greater than PE. And Hale, because Hale, the expected payoff of approve is well greater than the expected payoff of reviews. it means if the platform can get the probability PG directly, but maybe it is very difficult for the platform to get the probability PG directly. So maybe we can use other method. For example, we can use XGBoost. Okay, we can use XGBoost. Then the platform can get PXGB. Okay, we denoted the probability which is predicted by XGBoost by PXGB. Okay, PXGB denotes as the prediction of PG by XGBoost. And if the platform can get the prediction of PG by PXGB, then it can approve if PG, okay, if PG, okay, if PXGBoost, okay, here maybe it's wrong, PXGBoost is greater than PE. Okay, so we use this theoretical analysis and statistical learning to do an experimental analysis. Okay, the data is offered by an internet financial platform, which is including 13,000 samples, and here training set means including 24,000 samples, and the neighbor including 2 types: repay online on time or not. And every sample including 7 features: working city, salary, education level, marital status, etc. And we suppose the interest rate R equals 20%. And then we can compute PE. The probability of equilibrium is 0.8462. And on training set, an XGBoost model is learned as finger. Okay, maybe finger omitted. Okay, the test XGBoost of each applicant can be got by the learned XGBoost, and some predicted results are showing. Okay, maybe here is the finger. Okay, finger 3. This is the learned XGBoost model. It means, for example, for this one, the learned XGBoost is a boosting model, and here, for example, the first tree means x6 if it means the optimal splitting feature is x6. If x6 is less than 11, okay, then we will determine the value by the next splitting feature x4. Okay, x4. Okay. If x6 is greater than 11.
您可以稍微快一点。
Okay.
好的，谢谢。
Okay, so that's the model, and by this learned model, we can get the XGBoost. Okay, PE is the same for all the sample. PE is the same, and XGBoost it depends on the sample, and we know if PXGBoost is less than PE, we will suggest the platform to review the application. And if the XGBoost is greater than PE, we will suggest the platform to approve. Okay, and so on. By comparing column 2 and column 3, we can do the choosing of a strategy. The confusion matrix of learning result on testing set is about this one. And we can get the index APRF1. And results of empirical analysis show that this game theory based on Hassani transformation has a great performance. Okay, so next one we will conclude our work. First, we proposed the Hassani transformation driven by XGBoost, which is a statistical learning method. And the second one, we analyzed internet finance leading by game theory. The third one is in the empirical analysis, Hassani transformation driven by XGBoost is specifically applied to the internet funding leading. Okay, so thank you for listening and welcome your communication. Okay, so that's all for my sharing.
Thank you. Thank you. Very good presentation. Thank you. Anybody has a question?
I have a question. Do you have a list of literature, bibliography, the papers which you use in your report, the list of papers you use?
Sorry, 我没有听清楚，能不能您帮我解释一下？
您有没有引用的使用的一些论文的列表文献？就是
这里没有写出来，我的文章里面有。
Здесь нет, но него публикация уже есть.
Yeah, because you see, there is a famous paper of Harald Kuhn, called Extensive Games and the Problem of Transformation. This paper was written 20 years before Hassani, and the structure of the game was first introduced there with incomplete information. So I think you have to mention Harald Kuhn on the first place, and also after. But the presentation is very interesting. It's from practical point of view, I think, very important and interesting. Yes.
你能不能解释一下？我没听清楚。
他是说，是有一个什么东西，我也没听清楚。但是，您的报告非常好。有哪个同学、老师听清刚才教授说的话了吗
？Hello。
好像是说，就是这个20多年前，这个 Quinn 的教授好像是提到了一些什么东西。如果这个老师在做这个相关的东西来说，他应该把这个人的这个工作放在第一个位置上，就是引用他，应该这么说一下。
对。
Okay. So thank you for Professor. I will reference the literature you mentioned just now. So thank you.
Thank you very much for an interesting presentation. I have a question. So you use a kind of Bayesian updating for a static game, right? It's a kind of no, okay, it's not a static game, right? It's a multi-stage game, right?
这是
Yeah. So
他说是一个多阶段的。
是的，他们是多阶段的，是吧？不是个随机的博弈，是一个多阶段的过程。
这里no, it's just one step. One
step. Okay, no problem. Yeah. I think next month I will present a work for the Bayesian updating for dynamic type of games. I think it will be very interesting from theoretical point of view, but I was interested whether the dynamic Bayesian updating model can be could be important for you, because you have a very specific, very interesting application. So I'm interested whether you need this kind of dynamic Bayesian updating in dynamic case. So whether in this platform, in this internet financial platform, whether you have dynamic or all actions there are kind of, or all cases there are kind of static. Someone comes and then he wants to do something, that he goes away, or it's a kind of dynamic process. So I'm very interested. Could you please
next time
教授的意思是说问我去做动态博弈的是吧？贝叶斯的动态博弈是这意思吗？
他下个月的时候会做关于贝叶斯的一个报告。
哦，那我很感兴趣。
У нас что ты заметил, не слышал?
Я хотел спросить, вот она использует байесовское обновление в статическом случае, да? Я точно не понимаю, как это происходит, да? Ну вот как она использует, да?
Да, хорошо.
У меня вопрос. Нужна ли ей динамическая игра? Будет ли ей интересно применить ее метод, когда у нас есть не статическая игра с байесовским обновлением, а динамическая игра с байесовским обновлением?
Да, понятно.
Есть ли смысл ей применять такое или нет? Потому что в следующем месяце мы сделаем такой доклад на эту тему, а можем уже скоро сделать доклад. Вот. И мне интересно, можно ли применить, вот, потому что у нее очень хорошая модель.
Да, понятно. Динамические ситуации, правильно?
Динамическая байесовская игра
да.
с динамическим обновлением belief.
Да, хорошо. 就是他说这个前面说什么来着？前面是说您这个使用的是这个贝叶斯的过程，对不对啊？在这个过程中，他是想知道这过程是怎么发生的。然后第一个问题，第二个问题是他就是您刚才理解的，就是他想问对这个动态的贝叶斯过程有没有兴趣
？Yeah, thanks for Vilas, Professor. I'm very interested in Bayes dynamic game, but just now I just did not do some research. Maybe I will be very interesting to do the further work about Bayesian dynamic analysis research. Hell, for this.
Okay,
for this
I want to. Sorry, I want to do it with you. I'm not recommending for you to do this. I want to do it with you. So,
okay, it's very good.
Okay. Okay.
Very good.
We can present some results to you a little bit later. I think we can contact through Dr. Lin. Thank you very much. Thank you.
Okay, so thank you very much.
But I have a short question. Is it important for credit loan game or dynamic? Do you need dynamic model for credit loan game? Or
credit loan game.
就是您现在这个幻灯片展示这一页，如果做动态的可以吗
？Maybe, yeah. We can take account into more factors or components. The game can become a Bayesian dynamic game, maybe.
Okay. Thank you very much. This is a very interesting presentation. Thank you very much. I hope to see you next time at after 1 month at the seminar as well, and very happy to continue cooperation with you. Thank you. Thank you.
Okay, so thank you for your invitation.
Sorry, I have a question. Okay.
Please.
In this table, this slide, why letting platform select refuse and applicator select a better credit. The result is D. Because if letting platform refused, it doesn't. It should be 0.
Because I take into account the opportunity cost.
Opportunity cost.
Yeah.
Refused the bad credit, lost D.
Yeah. So if he did not refuse, he will lose. He will lose the 他会失去这个本金。
对对。
因为他是一个坏信用的人，你把钱借给了他，他也不会还给你。所以他就相当于是挽回了这个损失。
对对对，这样理解是对的。refuse 就是他拒绝，就等于没有失去这部分，那所以就是 D。对对，好的，谢谢 ，Thank you。
Thank you。
Thank you， 还是中文好。Okay, thank you for Professor's presentation, and next presentation is from Gong Ruifeng. He is a PhD student from Shanxi University of Science and Technology. His report is Green Supply Chain Decision Model for Engineer Saving Products that accounts for government subsidies. Thank you.
Screen. 有声吗
？OK， 都能，
谢谢。Hello everyone. Good evening. My name is Gong Ruifeng. I'm from Shanxi University of Science and Technology. Currently, my team is researching on sustainable development, environmental issues, emissions, logistics, and so on. Today, the topic I want to share with you.
Надо прекращать, это невозможно подряд. Это уже все разбежались.
Green supply chain decision model for emergency products that account for government's subsidies.
Не надо делать напряженно, понимаешь?
On this topic, I want to start with the following four.
Я себе думаю, он тоже думает. Ну молодец, хорошо. А реально из русских кто был, кто присутствовал?
Four aspects. Okay. The first one, for introduction, the second two, for problem definition and assumptions. Second three, model construction and solutions. Last one, conclusions and suggestions for future research. Okay, for first one, introduction. From the perspective of both theory and practice, sustainable development is a very important issue. The concept and the problems of sustainability are realized in many supply chain relationships with the government and the public increasing demanding environment protection. Producers within the product supply chain must increasingly pay attention to their environmental performance. Two, effectively implemented the United Nations Framework Convention on climate change. China's government submitted its intended nationally determined contribution to describe its enhanced action to combat climate change. So China promised to reduce carbon dioxide emission per unit of GDP by 6% to 6.5 by 2030, compared with 2005 levels. This one. It's true. Since the 1990s, China has adopted measures to guide enterprises and residents to shift their energy production and consumption toward energy conservation and emission reduced. For example, the People's Republic of China introduced the environmental protection tax law in 2018. For this, we found that at present, there are two main ways of government's subsidies. Because due to lack of funds, producers find it's difficult to fund research and development that leads to green innovation to produce more environmental friendly products. Therefore, it is difficult for producers of these products to own favorable competitive position in the market, resulting in sufficient motivation for enterprise to produce produce. So we found there are two main ways of government subsidies. One is to subsidize manufacturers to promote the productions of energy efficient products. Second, subsidies consumers to guide the consumption of energy-saving products. However, the effect of the two-sided methods on the production and the marketing of energy-saving products is controversial. Why we appeared this way? Energy conservation is a social problem involving governments, enterprises, and consumers, which needs to consider the interests multiple stakeholders in different situations. What to do for this? Just one. The coordination contracts is considered in supply chain of energy-saving products, and the enterprise profit in the supply chain can reach the maximum effect through the coordination of contract. Two, the degree of products energy conservation is one of the main factors affecting the market contracts, market demand. Demand. 3, we should not only study from the perspective of the enterprise, but also from the perspective of the supply chain. Last one, we need to discuss from the perspective of the government how to set a operational benchmark energy saving degree in order to effectively achieve a balance between social benefits and corporate profit and achieve the optimal social welfare. So in solve this problem, we give the 4 assumptions. First one, the cost for manufacturer to produce energy-saving products is same. The sales cost is CR. The wholesale price is omega. The retail price is P. And so P assumption two. The retail price and the energy saving level of the products are linearly related. According to review of the literature, we can look this paper. We are sure according to our view of the nature, typical demand functions is dp gamma equal a minus b needed p is so to improve the energy saving levels of products, manufacturers must increase the sale rate investments. This we find some numbers. Assumption 4: the government provides production subsidies that we are proportional to the energy saving levels of the producers and the governments for each unit of production subsidies cost. Is key. Multiplied gamma. So this is assumption 5. The governments provide manufacturers with subsidies to promote the production of energy-saving products, both to improve energy conservation and to maximize social welfare. The social welfare function can be expressed as a consumer surplus surplus CS surplus plus producer plus PS minus the total government subsidy cost as follow this. So we construct this models based this assumption. For example, the manufacturer's profit function can be obtained in funnel. As the returner's profit function is expressed as funnel. The profit function is expressed as funnel. So we can this as funnel. So we construct 3 models separated centralized decision model, decentralized decision model, coordination decision model for a two-way revenue sharing contract of this. So we can, for centralized decision model C, centralized decision making is a theoretically ideal decision method. This goal is to achieve the maximum profit for each member in the supply chain and thereby maximize the overall profit of the supply chain. This some results for centralized decision. Decentralized decision model, we call it model D. In decentralized decision making, the decision preferences of all members are risk nature. The decision making process is carried out according to the maximizations of each stakeholder's own interest. This results of the decentralized decision making of this. That's what we compared these models. From this analysis, we can infer that the result of centralized decision-making supply chain is more nearly ideal. However, in reality, it is very difficult to achieve a company centralized decision-making situation. So enterprises will always choose, because enterprises will always choose the most appropriate mode of operation according to their own operating conditions and needs, and will make decisions independently. If if manufacturers and returners both make decisions in this manner, then the total supply chain profit is less than the total under centralized decision making, which results is a double margin effect. Moreover, under decentralized decision making, the energy-saving levels of the products and the market demand for the product are both lower. Thus, decentralized decision making not only decreases over profits, but it also far to motivate manufacturers to improve the emission saving level of their products. Okay, to solve problems, it is obviously necessary to introduce other measures to coordinate the whole supply chain.
Okay, thank you very much. I think you have maybe 1 or 2 minutes left.
We can trust coordination decision model for two-way revenue sharing construct. We call it CD. In this section, we developed a revenue sharing construct model in which manufacturers and returners revenues can be shared directionally with the goal of modifying decentralized decision making to achieve the several results of centralized decision making through improved coordinating of supply chain. So we use these models. But these models we have results revenue sharing for this. In the process of coordination of the supply chain by means of revenue sharing construct, manufacturers and returners can adjust the value of the contrast parameters to determine the profit distribution within the supply chain. We can look this paper. This paper is that this. So we have this models results from position 1 to position 5. It is.
I'm very sorry. I think the time is limited. Maybe you could conclude. Maybe you could say some conclusion for maximum 1 minute, and then we could move on because time is a little bit short.
$10分钟。哦 ，OK。
就是现在已经你就是时间到了，因为也一直在延迟，所以想请您就可以简单的总结一下。不过我看好像也马上结束了。
OK，Thank you. Through the three models, we have our results. For conclusions and suggestions for conclusions. Our analysis related the following. Just one, in section 1, the energy-saving levels, market demands, and the total supply chain profit for energy-saving products were highest under centralized decision making. However, the retail price of energy-saving products was highest is in decentralized decision making. Is that true? Conclusion 2. With increasing government's subsidies, the market demand, the energy saving level of retail products, and the total profit of supply chain increase. 3. An income story construct between manufacturers and retailers improve the total supply chain profit, so that the profit under decentralized decision making increase to the same level as in centralized decision making. Last. To encourage consumers to purchase more energy-saving products, thereby improving profit for both manufacturers and retailers. Both stakeholders should implement review sharing. Thank you. That's all. Thank you. My communication is over. Thank you for your listening.
Thank you very much. Thank you very much.
Anyone has a question? Anyone has question?
No questions. No questions.
Okay. Yes, in Yes Plus 如果没有问题的话，我们let's start next presentation.
Thank you. Okay.
Thank you for your presentation. And next presentation is the last presentation on game theory section, and this presentation, the presenter is Ye-Pei Chen and Chen Min. Chen Min will be reporter, and their supervisor Organas and me, and their title presentation is the overview of dynamic minimal cost spinning tree games. So please share your screen and start your presentation.
Oh, okay, Professor. Good afternoon, everyone. Welcome to my presentation. My name is Chen Min. What I want to report today is the overview of dynamic minimal cost spanning tree games. This report was completed by Ye-Pei Chen and me. This is the framework for minimal cost spanning tree game. In 1957, Prim began to study the spanning tree algorithm and raised research questions about spanning tree. And then Klaus and Klettman first proposed minimal spanning tree game in 1973. Bird proposed a reasonable allocation method based on cooperative game, which named Bird Rule, and proposed a reducible form at the same time. So in 1993, Arts and Dresden have more research on a reducible form, and Bergantin considers using the perspective of non-cooperative game to research the minimal spanning tree problem. Daniel Granout and Gur Huberman proposed a reasonable allocation method based on cooperative game. They gave a second solution for minimal cost spanning tree games, and they also proposed more research on game theory structures, such as core and nucleus. In 2002, Carr introduced and described the Shapley value of the independent cost games related to the minimal cost spanning tree game, and Bergtinoz referred the Shapley value in a reducible form because bird rule don't have some properties. So there is a third solution named Folk rule. It has many good properties, such as solidarity, population, monotonicity, and so on. The first part will introduce what is a minimal cost spanning tree. The minimal cost spanning tree is a spanning tree with the smallest weight in a connected, weighted, and undirected graph. In a give graph G, Ij means the edge connecting player I and player J in the game, and Cij means the cost of this edge. If the formula Tx holds, then N apostrophe is graph J's minimal cost spanning tree. In 1950, American computer scientist Robert C. Prime independently discovered an algorithm for finding the minimal spanning tree called Prime algorithm. Each step of Prime's algorithm adds an edge to a growing tree, which has only one vertex at the beginning, and then adds v minus 1 edges, always at the edge with the least cost of the spillet formed by the growing tree and the part of the tree other than the growing tree. Prime then proved that any tree resulting from the algorithm is a minimal cost spanning tree. Note that by varying between the possible edges in step 3, this algorithm can construct all minimal cost spanning trees of this minimal cost spanning tree problem. Let's take a look at the first example. To insert optical cables between 7 cities, it is required that any 2 cities can communicate, and the cost of inserting optical cables between cities is different. So the total cost of inserting optical cables should be minimized. Here you can choose D as the starting point and choose A as the minimal cost connected to D in the set of optimal vertices. In the set of optimal vertices, the minimal cost of choosing D or A is F. Repeat the above process until all vertices are selected. The resulting of minimal spanning tree is shown in the figure. In 1973, Klaus and Clayton proposed the concept of minimal cost spanning tree games. Giving a set N of players whose power set 2n like this is the set of coalitions. A function C with the empty set equals 0 is the characteristic function of the game. The characteristic function of the minimal cost spanning tree NC is defined by this. A problem related to a optimization problem is how to allocate the cost of the edge of a minimal cost spanning tree among the players in a reasonable way. In 1976, Bird Associated introduced it minimal cost spanning tree game to a minimal cost spanning tree game. The players are the agents, and worth of a correlation S is the minimal cost of a tree on S apostrophe, like this. This formula holds for all S, but also proposed a cost allocation rule for the minimal cost spanning tree problem, which he calls the tree allocation rule, because it associates a cost allocation to every minimal cost spanning tree of the minimal cost spanning tree problem. If the minimal cost spanning tree problem contains two or more edges with the same cost, there might be more than one minimal cost spanning tree. And for a particular minimal cost spanning tree, NT, it can happen that there is more than one order in which Prim's algorithm can choose the edge T. Obviously, the order does not change the edge that a player has to pay according to Bird's tree allocation rule. So Bird's tree allocation is independent of the order in which the edges of the tree are chosen. It does, however, depend on which tree is constructed. See example 2. In the problem on the left figure, whether Prim's algorithm chooses the links in the unique minimal cost spanning tree in the order 0, 1, 0, 2, 2, 3, or 0, 2, 0, 1, 2, 3. In the problem on the right of figure 2, only one of the two dashed links will be constructed. In case 0, 1 is constructed, Bird's tree allocation is 10, 5, 6, and if 0, 2 is constructed, Bird's tree allocation is 6, 10, 5. In 1981, Daniel Granold and Gore Huberman turned the problem of cost allocation among users of a minimal cost spanning tree network into a cooperative game in characteristic function form. It's referred to as a minimal cost spanning tree game. They show that the core of a minimal cost spanning tree game is never empty, and that the nucleolus of the original game is the Cartesian product of the nucleoli of the minimal cost spanning tree games defined on the component of the structure. They followed up with further studies of the core and the nucleolus and gave two efficient procedures for generating cost allocation vectors in the core of a minimal cost spanning tree game. And the car gave us an axiomatic characterization of the Shapley value, which more suitable for the minimal cost spanning tree game. He gave the important theorem as follows. Now look at this example. Corresponding to C, the set of agent is partitioned as n equals 1, 2, 5, and 3, 4. The edge 1, 2 is not relevant. Therefore, the allocation per se coincides with the Shapley value phi. So we can see each player's Shapley value like this. In C apostrophe, the cost of 1, 2 decreases to 1, and the cost of other connections remains the same. Both 1, 2, and 3, 4 are relevant. We can see the Shapley value has been changed. In 2007, they gave another solution to solve the minimal cost spanning tree game. They proposed a reducible graph corresponding to the Shapley value of the game. Here is an example. First, we found a minimal cost spanning tree like this. Because the cost of each edge in the figure is defined as the cost of the edge corresponding to the most costliest edge in the two-node path under the minimal cost spanning tree. So we change the graph, becomes a reducible graph like this. Now we talk about dynamic minimal cost spanning tree game. It has two situations. One is about graph structure. The other is about player's choice. This is the case considering the structure diagram in Lin's article, the dynamic Nash bargaining solution for two-stage sharing game. The change of the structure diagram was mentioned in this article. The concept of transition probability P is proposed. It means that the probability of the game moving from initial vertex Z1 to Zk and the probability of moving from Z1 to each vertex is equal to 1. And assume that each vertex Zk is associated with a matrix called alpha matrix. The alpha matrix of the stage game in vertex Zk is defined as follows. Then the method Hadamard to give the matrix stage game in the vertex Zk. The cost matrix depends on two parts. The first part is the alpha matrix. The second part is the cost matrix, like first stage. Let's look at the figure 3. From first stage to second stage, if all players select strategy X01 in the first stage, there would be different transition probability in second stage. In this example, in first stage, the minimal cost spanning tree like red one, like this, and another minimal cost spanning tree is the green one, like this. And then this is the second situation of the dynamic minimal cost spanning tree games, whether players continue to participate in the second stage. Here is a new definition of the characteristic function, Vk. And we have an important theorem about time consistent like this. Now we can look at this example. This is a 3 players 2-stage game. Alpha square is a discount parameter in stage 2. In this example, it equals 1.5. The cost of H10 in the graph in stage 1 equals the cost of H10 in the graph in stage 2 and equals 1,000. The cost of H20 in the graph in stage 1 equals the cost of H20 in the graph in stage 2 equals 1,500. The cost of H30 in the graph in stage 1 equals the cost of H30 in the graph in stage 2 equals 1. This is the profile strategies for each player in different stage. In one stage, players choose strategies profile and build a minimal cost spanning tree. that the total cost of this tree is minimal between all possible spanning trees, like this. C13 equals x13 multiply x31 and equals 10. And we can use the same way to get the cost of each edge. So the sum of cost of spanning tree in one stage equals 25. Similarly, in two stages, players choose strategies and build a minimal cost spanning tree like this. In this stage, the edges 2, 3 will be discounted. So the sum of cost of spanning tree in two stages equals 71. And the total cost of in two-stage games equals 25 plus 71. It's 96.
这里可以快一些啊。
This is the references for this report. That's all. Thank you.
Okay. Thank you for your report. And anyone has a question? 大家有什么问题吗？这个是关于最小生成数博弈的一个问题。喂，好的，谢谢，thank you for your report and Omenas.
Yes, hello.
The section about game theory is over.